Okay, so we'll proceed with optical properties of conjugated semiconductors. So up to now we covered, the last thing we covered was the quantum yields, how to calculate the quantum yields. And now you'll be introduced to Einstein coefficients. So Einstein coefficients are mathematical quantities that are used to talk about the probability of an event happening. And the events can either be absorption, emission, i.e. spontaneous emission, or stimulated emission, when light interacts with an atom or a molecule. For spontaneous emission, we use the coefficient A, and for absorption and stimulated emission, we use coefficient B. So when photon absorption occurs, photon is absorbed by an atom. It causes an electron to jump from the, in conjugated polymers, from the HOMO to the LUMO, or from the lower level to a higher energy level. And the process is described by the Einstein coefficient of B 0, 1. Sometimes the subscripts can be different, but here we're using 0, 1. It has units of meters cubed per joules per second square. And this coefficient gives the probability per unit time per unit spectral radiance of the radiation field that an electron in state 0 with energy E1, let's say, will absorb a photon with energy E2 minus E1. And then as a result, it jumps to a state 1 with energy, which has energy 2. The change in the number density of atoms in state 0 per unit time due to the absorption is given by this equation. So dN by dt, and n has to be n of the initial state, so for us it's 0, equals minus the coefficient, Einstein coefficient, times the initial number of carriers, number of atoms that were in the ground state, times the spectral energy density of incident light. Similarly, we can describe the probability of events happening for spontaneous emission or stimulated emission through Einstein's equations, and then from there write the equation for the change in the number of density of atoms in each state. From this, we can go further and talk about oscillator strength. So as I have so far only casually described what is an oscillator, I mentioned the word oscillator strength. Now we get to see what it really is. Oscillator strength actually means the strength, for instance, the strength of the coupling between, let's say in the absorption, the oscillator strength of absorption would be the strength of coupling between a dipole and the electromagnetic field, so your light, relative to the standard oscillator consisting of just a single electron mass, ME. So here we're saying that basically the Einstein equation going from level 0 to 1 would be the same as the Einstein equation, coefficient going from level 1 to 0. And we relate the Einstein coefficients of A and B. So here we said A is for the spontaneous emission, and B was for either absorption or stimulated emission. And the relationship between the Einstein coefficients A and B is governed by this equation. Now we know that the Einstein equation B is related to the oscillator strength of a particular transition through this equation. So F is the oscillator strength. This is your Einstein equation. and it depends on the mass of the electron and several other parameters. So the final oscillator strength can be calculated from the spectrum of the molar extinction coefficient, and it involves integrating your extinction coefficient parameter, EM, over your entire spectrum, the spectrum that you are interested in. So all of this just comes from the constants that we have. We also know that we've said that A naught is the coefficient for spontaneous emission. Emission means it's radiative transition. So we have a particular rate or particular lifetime. So rate and lifetime are inversely related to one another. And this is saying the rate of radiative transition equals to the Einstein equation coefficient for spontaneous emission. So putting everything together, we get the Einstein coefficient is actually related to the transition dipole moment via these equations. And we also get an equation relating the oscillator strength and the dipole transition moment. So if you remember when we were talking about the intensity or the strength of an event absorption happening, when we talked about the Frank Condon principle, I mentioned the transition dipole moment. Again, we haven't done any of the quantum mechanics maths part of it to reach this equation, but you need to know these equations while you're not expected to know the derivation of them. But what it's saying is that this is your transition dipole moment, and the stronger this is, especially it's because it's squared, the stronger the strength of a transition happening would be. And this would then mean that if you have an absorption, for instance, that peak for that absorption will be stronger if F is stronger, so the intensity of it will be higher. Okay, so now concentrating on radiative processes, we said that if you go from S0 to S1, in S1 this is not stable condition, so eventually after some time the excited source wants to come back, relax back to the ground state, and this mostly can happen through fluorescence, where it would be radiative. Now we can estimate the number of molecules and the change in the number of molecules in the starting point and the finish point. So here we have N1 molecules in the excited S1 state, and they go through spontaneous emission to come back to the S0 state. The equation as we had here is just relating the change in number and the carrier density through the Einstein coefficient and multiplied by what we initially started with. So just by integrating, forming this is your integral equation, you integrate both sides, you get N1 as a function of T equals N1 at time 0. So this is when everything's still in S1 state, there is no decay back to the ground state, times an exponential term which shows the decay of the carriers back to the ground state. In the last slide, we said that A10 equals Kr, so the rate of the radiative transition. And this itself, it equals also 1 over lifetime of the radiative transition. So we can either write this equation in this format in terms of rate or in terms of lifetimes and time. So now you can see with what sort of time scale, half-life, the number of molecules in the excited state will change to the ground state, for instance. Yeah, this goes back to the quantum efficiency, quantum yields. So we're saying we have spontaneous emission only, so the excited molecule emits a photon. Yeah, exactly. So your quantum yield or your flux of emitted photons can be calculated. And this is all, I think, yeah. So here, the number of emitted photons equal the number of initially excited molecule because we have spontaneous emission, right? So n photon equals n1. This is an example of some oligofluorines where the repeating unit has been changed. So when we don't have really large number of repeating units, we call it oligomers. Otherwise, when it's really large, we call them polymers. That's the difference. In this table, we have the information about where they absorb, where their PL is. So the difference between the two would give you your Stokes shift. And this is your dipole transition, your dipole moment transition, yeah. And the lifetime of your radiative states. And what it shows is that as we increase the number of repeating units in the oligomer, then the lifetime, the radiative lifetime becomes smaller. This could either be because we end up having more non-radiative processes competing with your radiative, or it could just be that actually when it's in the excited state, so when we are here, it takes a shorter time for it to come back to the ground state. And you can see this trend here, lifetime versus 1/n. So as n increases, lifetime gets smaller. Hold on. Okay, so in the table, the table, I said we can have two things, either that the lifetime is getting shorter because they're just not that long lived, or maybe we have another competing process which is non-radiative. So it means that you have some radiative emission and you have something else which doesn't show as radiative, it's non-radiative. So here we're considering both an additional channel, which is non-radiative decay channel. And now things get a little bit more expanded. Now our rate equation for the number of carriers at any time after they leave S1 have to consider, obviously you had your radiative rate, now we have to consider all the non-radiative terms. One term is with internal conversion, the other one is ISC, intersystem crossing. We can also have vibrational relaxation, but these two are the ones that, well, as we said, vibrational relaxation happens really fast. So these two have more similar lifetimes or rates. So these are the ones that contribute. And then we term these two, or we term all of the ones that contribute as non-radiative. So now you have a term for radiative, you have a term for non-radiative rates. And then the integration doesn't get any more complicated or anything. It's just basically, instead of just having a simple KR, now you have something in bracket. So now you have the number of carriers at time t equals your initial number of carriers in S1 state times the exponential term raised to the power of minus the time at any one instant that we're monitoring the system over the entire lifetime of the excited state. So we call that TF. This TF includes all the radiative processes, all the non-radiative processes. And so the fluorescence lifetime now is 1 over a sum of radiative and non-radiative channel contributions. So if this is increasing, but this is not changing, then your overall, your TF decreases. And that may very well be what's happening here. Our TF is decreasing, which may suggest that it's not that this is getting smaller, but perhaps this is getting larger. Okay, fluorescence quantum yield. The quantum yield we have already talked about. It's basically the number of events that happens as a radiative channel over the total. So KR is 1 over TR, and KR plus KNR equals 1 over TF. That's why you got this inverted fraction here. And usually in most systems, this fraction is smaller than 1. Excuse me. So in an ideal case, this would equal 1. In the majority of cases, we have a lot of non-radiative losses as well. In most cases, non-radiative losses are not a good thing. So that's why I say in an ideal case, this quantum yield would be 1. So here is an example of one system, and we look at the quantum yield as we go from solution to a film. So in solution, the quantum yield is about 60%, 70%, close to 70%. But as soon as we go into a film, oh, hold on. Yeah, this is now percent, exactly. So this is rather sloppy because the units are somewhat different here. This has been turned into percentage, whereas this hasn't. So anyway, this is 64%, 69%, and so on. Here you have 15%. So you can see you have a big drop in the quantum yield when we go from solution to the film. Any guesses why? And when we go, this is rather consistent. It's not just for this example. Usually as we go from solution to film, we lose quantum yield. Any guesses why that might be? It's because when we make a film, we increase the channels for, say, aggregation or self-trapping. And most of these would actually have non-radiative transition. For that reason, your quantum yield of fluorescence goes down. So here's a table to give you an idea of efficiencies of PL for different polymers. So now you know this P3HD. I mean, to begin with, okay, let's look at the PL quantum yield. They are all very low. Yeah, they're all very low. But in general, there is not a good understanding between the molecular structure or crystallinity of it with the PL quantum yield. But most of the conjugated polymers, they have very low PL efficiencies or the quantum yield efficiency. Okay, so now we are on exit on migration. Yeah. Okay, so now let's imagine instead of having just one molecule, most of this time, even though we had polymers in mind and everything, we were only considering what happens when we have one molecule or one atom, one molecule, one part is only excited and it has no interaction with anything else. That might not be the only thing that's happening. So in one case, we might actually have an electronic excitation from one chromophore to another chromophore. Yeah. And so far, we've been talking about intermolecular transfer, but something else we can actually talk about is that when we have a large molecule, we can also possess two chromophores. So in that case, we can actually transfer energy through intramolecular energy transfer. The idea is that we excite one chromophore, one donor, one atom, one monomer unit. The excitation of this molecule is passed on to the second system, whatever it wants to be, whether it's an acceptor, whether it's another monomer, or so on. And now the acceptor chromophore wants to lose this electronic excitation that it has gained through the energy transfer. It can do so through fluorescence. So we excite this, the energy gets transferred to your acceptor, and then it fluoresces. If we have absorption, so even if we do, say we have an emission or a fluorolog to look at the emission of these materials, if we had no energy transfer, when we excite this, we would just see the emission of this system. But in the case where we have energy transfer, we have excitation of this, but rather we end up in monitoring the emission of the acceptor. And this process is known as the Forster resonance energy transfer. And the one requirement that we need to have is that the absorption of this system overlaps with the emission of the acceptor. So you can see you have some overlap here. In order to have this overlap, we also need to have there's a requirement for the distance between the two systems. Okay, I don't have the equation here, but basically it's r to the power of 6. So the efficiency of transfer is given by r to the power of 6 divided by the total, divided by, let me just say, r naught to the power of 6 plus r to the power of 6. What is r naught? R naught is the characteristic distance between the donor and acceptor. So you can actually, even one other thing that we can do, you can also determine the efficiency of FRET, the energy transfer, by comparing the fluorescence quantum yield of the donor system in the absence of the acceptor, and then compare it with the fluorescence quantum yield of the donor once the acceptor is present. So the quantum yield of when the acceptor, so when this situation is happening, would come on the numerator, and the fluorescence quantum yield of this will be on your denominator, and this will give you the efficiency of fret occurring. Okay. Something else we can have is, so all of these are ideas that after we have excited the system and we've taken it to S1 level, what are all the possibilities thereafter? So first we talked about relaxation of the states back to the ground state through either fluorescence, or if it did intersystem crossing to triplet state, then phosphorescence of that to the ground state. Now we talked about energy transfer. Another possibility is essentially an exciton will diffuse to a certain distance away from where it got excited. So we excite from HOMO to LUMO. If it's an organic system at room temperature, we have strong Coulomb attraction, so the carriers are not free, but they are bound to each other, and that's what we call exciton. Now the exciton has a high tendency, because it has the Coulomb attraction, it has a high tendency for it to relax back to the ground state. But before it does this, it has a certain lifetime that it can live in the excited state before it comes to the ground state, before it decays to the ground state. And in this within this lifetime, the exciton is a neutral particle, quasi-particle. It can diffuse to different or random even directions. Given that the process of the movement is happening through diffusion, it means we need to have a concentration gradient. So it will diffuse from regions where there's high concentration of quasi-particles to regions where there is none. And the distance that the exciton can take or can travel within the lifetime that it has equals the exciton diffusion length. So the exciton diffusion length is the distance an exciton can diffuse before it relaxes back to the ground state. So in this paper, they looked at the exciton diffusion length of MDMO-PPV, which is another system that was studied before Q3HD. And they saw how the exciton diffusion length, which is this parameter here, just as a function of temperature. So at room temperature, we have relatively higher exciton diffusion length, about 4.5 nanometers. As we take the temperature down to 0 Kelvin, the exciton diffusion length reduces down. As you can see here, no, this is the PL position peak, okay. Maybe I won't go into too much detail, the dependence on the temperature, because it goes back to the fact that we have trapped states and what happens if you're trapped and so on. So it's related to the fact that we have a inhomogeneous energetic distribution in the density of the state, or of the density of state. And because of that, we have some trapping and detrapping when we don't have enough thermal energy to make the detrapping happen. Obviously, the charges get stuck. So if the exciton diffuses to a, within the exciton diffusion length that it has, if it diffuses to a particular position where there's a quencher, then we can quench it. What does a quencher mean? Quencher means it's anything that it reduces or quenches the species that we have. So in this case, exciton. So for instance, if I have a donor and acceptor, this time if fret is not happening, what the alternative that can happen is that the exciton will diffuse to the interface. The acceptor, which has a lower energy level, so let me just bring this up. Lower energy level. This is not a good drawing. Anyway, it has a lower energy levels. Will attract the electron on the exciton, and the electron will transfer to the acceptor. That's one thing that can happen. That's the electron transfer. As we talked in the last slide, exciton migration to traps can also occur because we have trap states, so then they will get trapped. Exciton annihilation can also occur, and this is basically when two excitons annihilate each other. You also have photoisomerization, photooxidation, and so on. So there are a number of things that can happen when you're in the excited state before any emission occurs. So the first thing that, Excimers. What are excimers? Excimer, as the name suggests, is an excited monomer or dimer in particular. So here you have two monomers that are identical. We call them dimers. We excite one and we look at the emission. So here you can see that if you had a monomer, if you had just a instead of having a dimer, you had a monomer, this would be the emission of the monomer. But when you have a dimer and you excited the monomer unit of the dimer, then you form an excimer. So now you have the excited dimer, where one of them is excited and the other monomer is not excited, and you get the emission to be different. So you get it to be shifted, and also the vibronic level are no longer that apparent. There are many ways to change the intensity. So here the intensity of emission can change through concentration. And this is because when we have high concentrations, we can potentially have annihilation or self-quenching even. Another way of losing your PL intensity is when you have photooxidation. So a lot of our systems are actually sensitive to both oxygen and light, but in particular when both of them happen at the same time. And this is an example of what happens to the PL. The red data is a fresh cell which has not been degrading at all. And then you can see as time is allowed for light and oxygen to be bombarded on the polymer, PF, the emission is lost. So we have degradation. And it's not just that this emission intensity is lost, but rather we start to have actually a new peak forming. And this is because we have the photodegradation that actually results in formation of, so it breaks some bonds, and in this particular case, it forms a keto defect. And it acts as traps for excitation for excitons and electrons. And as a result, we get this new emission band appearing in. Okay, so let's carry on. Okay, the next thing that we'll just touch upon and quickly go through is lasers, polymer lasers. The medium material for lasers can generally be divided into either solid gain media, gas gain media, liquid gain media, and semiconductors. Semiconductor lasers are actually attractive because they can be a lot smaller, they have fast response times, they usually consume lower powers, and they have high efficiency compared with other types of lasers. The lasers that use semiconductor, especially conjugated polymers, can be prepared just like, say, solar cells, LEDs, or whatever, from solution from different ways. So in addition to luminescence efficiency of conjugated polymers not being affected by quenching effects of the concentration, the luminescence efficiency of the film, as we've seen, sometimes is actually affected. But as long as we keep the concentration low, then the quantum yield of the film is also maintained as we need it. So for a laser gain media, we need to meet the following following conditions. First, the conjugated polymer has to have appropriate energy level systems. So this is an example of an appropriate energy level system, which allows to achieve particle number inversion between the ground state and the excited state. The polymer system of interest should have high luminescence efficiency and high chromophore density. Some of the studies have shown that actually if the conjugated polymer side chains are not intertwined, then the PL quantum efficiency can actually be really high, even sometimes up to 60%. And the last requirement is that the absorption spectra cannot overlap with the stimulated emission. This will reduce self-absorption, but we need to make sure that absorption and the stimulated emissions do not overlap. Okay, so this is a 4-level energy system, and it can be divided into the ground state, excited state, a metastable state, and a final state. So from S0, the particles are excited. They jump from the S0 level to either 2. Well, yeah, initially they will jump to level 2, and then to level 3, which is then your state, S1 state. Then the particles in S1 are rapidly transferred to the metastable state, which is 4, through non-radiative transition. The excited particles, let's call them particles, can accumulate in level 3, so your S1 state, because as we said, the S1 state can actually be rather long. For organic conjugated polymers, we said about a nanosecond at least. So they can accumulate here because of the long metastable lifetime that they have. And then here is when they realize particle number is in inversion between this level 2 and level 3. So after we have this inversion, essentially this energy level is empty at room temperature, and the number of particles in the final state here is very small because the majority of them are here. So as long as the number particle in the metastable state is greater than the number of particles in the final state, then particle number inversion is realized. So stimulated emission and lasers. This goes back to the Einstein coefficient, which was B10, and we said that the Einstein coefficient for stimulated emission would be, you know, same as the Einstein equation for absorption. Yeah. One thing that we didn't talk about before is the cross section. The cross section basically tells you the probability, or how much, in this case, stimulated emission can occur per centimeter square. And here the idea is to, well, here is when we have the absorption. So when you do transmission, basically, it's through a gain medium. Is the transmission that comes out over the initial transmission, and that to the power, that equals 10 to the power of gain, which is G, times the depth of your gain media, so L. The gain itself, to give you an idea what it is, it's related to the cross section times the carrier, the volume, the volume of the carrier density. So how many particles can be stored in that volume? So here is some ideas, some numbers for typical polymers that we use. The gain G is about 10 to the power of 2 or 10 to the power of 3 per centimeter. So that means that 1 out of 100 or 1,000 chromophores need to be excited in order to get lasing happening. And the lasing threshold is given by this equation. So this is the threshold, P naught. It's proportional to the lifetime of state 3 times the natural log of reflectivity of the cavity. This is your cavity, divided by the absorption cross-section, the stimulated emission cross-section, the number of chromophores that we have, and to begin with in the ground state, and the length of the gain, the medium gain, the gain medium. Okay, I think this really has gone for so long. We will stop here. And I think, yes, this will cover everything for you. I will take the transistor section out, and other than that, yes, the entire syllabus is covered. So with that, I hope you've enjoyed everything, and best of luck for your exams.